This is the next theorem, which is the Norton theorem. First, I will discuss about basic points related to this Norton theorem, and then we will discuss about explanation part of this Norton theorem, and then finally we will solve the problems based on this Norton. This is great. I will read out the first statement. This theorem is very similar to the Thevenin's theorem. This theorem is very similar to the Thevenin's theorem. Only difference is that's why it is known as a dual. Thevenin's theorem and this Norton theorem are known as a dual of each other. Dual networks. This is right. Now look at here how will be the case. Now here in this case, how is the statement or what is the statement? For a linear bilateral active network, current flowing through the load resistance or load impedance is given by following expression. How is the expression? This IL is equal to IN into Rn divided by Rn plus RL. The circuit is a purely resistive circuit. And when impedances are there in the circuit, in that case IL is equal to IN into Zn divided by Zn plus Zn. This Rn or Zn, it may be Zn. This is resistance or impedance. That's right. Now, how is the statement? Is given by this expression. Expression is IL is equal to, it is IN into Rn divided by, it is Rn plus RL. We have to justify this, how it is. That I will show that in the explanation part. But what is IN? IN is Norton's equivalent current calculated at the output terminals when load resistance or load impedance is removed. Load resistance or load impedance is removed. This is right. Means what? If we have the circuit, in this case, if we will remove the load resistance, and here I will add, load resistance is removed and output terminals are shorted. Output terminals are shorted. Means we have to remove this load resistance and we have to short these terminals. And we have to calculate current in the short circuit, and that current is nothing but the Norton's current. Are you getting me? That current is the Norton's current. Finally, what is Zn or Rn? Norton's equivalent resistance or equivalent impedance calculated at the output terminals when the load resistance is removed and all sources are replaced with respect to intensity. Here, its name is different only. In the Thevenin's theorem, the same impedance or resistance is known as Thevenin's resistance, and in the Norton's theorem, the same value is known as Norton's impedance. Same value is known as Norton's impedance. If you are aware of the calculation of Zn, Thevenin's impedance, then calculation of the Norton's impedance is same as that. Is it right? Means again, the problems based on this theorem, that is Norton's theorem, can be solved in 4 steps. I will discuss the steps. But while solving the problems, we will not use the steps, or we will not mention the steps. What is the first step? I will try to show here. First step is remove the load resistance. Remove the load resistance and short the output terminals. Short output terminals. This is the first step. Second step is the calculation of IN, that is Norton's current. Third step is calculation of Norton's resistance, that is Rn. And final step is that whenever we know IN and Rn, then complicated network will be replaced by Norton's equivalent network. And how is the Norton's equivalent network? This network is known as Norton's equivalent network. This is load resistance which we have removed. This is Rn which we have calculated from here, and this is In which we have calculated as In. Means the source with this is Norton's equivalent network. This is Rn and this is In. And similar is the Thevenin's network. How is the Thevenin's network? It is something like this. This is Thevenin's network. This is RTH. This value is the VTH. Is it right? We can convert this voltage source into the equivalent source, then it will become Norton's. And if we are converting this value to this, it will become Thevenin's network. That's why this Norton's network is a dual of Thevenin's, or Thevenin's network is dual of Norton's. One and the same thing. Norton is dual of Thevenin's, or Thevenin's is dual of the Norton's. Means we can convert current parameters in terms of the voltage and impedance parameter in terms of the admittance. So that we will discuss later on, maybe in the unit number 5 or 6. Is it right? You see here, these are the steps, and I will use the similar steps for these calculations. I will use this first step. How is the first step? Removing load resistance. I will write the first step here. Step number 1. Removing load resistance and shorting. Removing the load resistance and shorting its output terminals. And shorting output terminals. We get. We will short the output terminals. How will be the figure? Figure for this calculation or explanation will be something like this. This is one part. This is another. Now this will be the figure for step number 1. This is A point. This is B point. Here it is R4. This is R5. This is R2. This is R1. This is R3. And it is the applied voltage, which is V. I will show you. It will be the figure. This will be the figure. So here in this case, this is the figure for the calculation of Norton's current. Is it right? Now in this case, calculate current in this branch, which is IN, that is Norton's current. Use any method. You can use the mesh analysis. This is loop 1, this is loop 2. Or you can use the nodal analysis. This is branch 1, branch 2, branch 3. You can find out that value. You can use the direct inspection method. This is loop 1, loop 2. Calculate its value, and find out. I will use here nodal analysis. In this case, it is node A having its potential VA. This is ground node. This current may be the I1. This current may be the I2, and this current may be that current which is IN. Is it right? Applying KCL at node A. Applying KCL at node A. If we are applying the KCL or Kirchhoff's current law at the node A, how will be the KCL? This I1 is equal to I2 plus IN. How is the equation for this I1? V minus VA divided by, it is R1 plus R3, which is equal to. How is the I2 current in this branch? VA divided by R2. This is VA divided by R2 plus IN. How is the IN current in this branch? VA minus 0 divided by this resistance, which is R4 plus R5. And this equation has only one unknown, and that unknown is the VA. That's why I'm writing the same. Solving above equation, we can find out VA. And if we know the VA, therefore this IN is equal to, or Norton's current is equal to, this is always the modulus value, or this is always the positive value. Just like a Thevenin's value. This IN is equal to, how much is this value? It is VA upon R4 plus R5. This indirectly we are able to find out IN. And if we know the IN, we can find out the value of Rn. Now look at here. This is second step. Is the calculation of second step. This is calculation of IN. Third step is the calculation of Rn. Calculation of Rn. And for the calculation of Rn, majority times we should not consider this figure as it is, because it is short circuited. Remove the short circuit, which is nothing but load resistors. Remove the sources by respect to internal resistors. Otherwise, refer this original figure. Refer this original figure for the calculation of. Refer this original figure for the calculation of Norton's resistance. How is the figure? Remove the load resistors, remove the sources. In that case, this figure will be something like this. This figure will be something like this. This is point A. This is point B. This is R4. Here it is R5. This is R2. This is R1. And this is R2. Is it right? Using this, we can find out its value of the Rn, that is Norton's equivalent resistance. How will be the Norton's equivalent resistance? These two resistances are in series combination. If I am drawing next figure, this will be the value. Here it is A point, this is B point. Here it is R4, this will be R5, this is R2, and this is RS, series combination. How much is the value? R1 plus R2 is that value. Now these are two parallel. I will call this parallel combination as a RP. In that case, that is RP. This is A point, this is B point, this is R4, this is R5. Its parallel combination will be the RP, and this RP is nothing but RS into R2 divided by, it is RS plus R2 is the parallel combination. And finally, we can find out the Rn, which is Norton's equivalent resistors, which is addition of all these. That is R4 plus RP plus R5 is the Rn. If we know the IN here, if we know the Rn, then complicated network is replaced by Norton's equivalent network. Norton's equivalent network. How will be the Norton's equivalent network? I will draw. This network is the Norton's equivalent network. This is Rn. This is IN, which is the Norton's current. This is IN, which we have calculated. Rn we have calculated. And reconnect the load resistance, which is removed in the step number 1, which is RL. No need to mug up the formula. Use the current division rule. If this current is IL, what is the formula for IL as per the current division rule? Total current, which is IL, into resistance of the opposite branch. In this branch, current is known. In this, we are interested, which is Rn divided by summation of both. That is Rn plus RL, and which is nothing but the Norton's network. If this is the formula, IL is equal to IN into Rn divided by Rn plus RL, or IN into Zn divided by Zn plus Zn, is the formula for the calculation of the load current using this theorem, which is the Norton theorem.